Your phone recognized you in less than half a second.
Beneath the screen sits a sensor that reads your fingerprint through glass using sound.
It sends sound waves through glass and maps your fingerprint from the echoes.
Unlocking, payments, passwords, and identity all depend on this sensor working every time. One feels invisible inside a phone. Factories build them by the thousands.
But almost nobody sees where fingerprint sensors are made. Today, we follow how ultrasonic fingerprint sensors are manufactured.
Before sunrise, Sora checks the sensor yield data from the night shift. She watches for weak spots because a sensor that fails once loses the user's trust.
At this scale, one missed pixel can mean a failed unlock.
Inside the fab, contamination control starts before the first tool runs. Like most sensors, this one begins on polished silicon.
But its key material is different, a piezoelectric film that converts electricity into sound.
Apply voltage, and it vibrates. Those vibrations become the ultrasonic pulses that read your finger.
Beneath the piezoelectric layer sits a silicon pixel array that captures returning echoes. A controller chip processes those echoes into the fingerprint image your phone compares. A flex circuit carries signals from the sensor to the phone's main board. Between the sensor and the display sits a coupling layer that transmits sound cleanly.
Nothing enters the line before dimensions and material properties are verified. Only approved materials reach the sensor production floor.
First, the silicon wafer is cleaned. Any particle here becomes a dead pixel later. Then the pixel array is built using standard semiconductor processing steps. Each pixel converts one echo into one signal point in the fingerprint image.
Metal layers connect every pixel to the readout circuit below.
Now the piezoelectric layer is deposited directly over the pixel array. Thickness controls the frequency of the ultrasonic pulse it generates.
If the film is too thin or too thick, the pulse frequency shifts and image quality drops.
A top electrode completes the structure that drives and receives ultrasonic energy.
Every die on the wafer is tested before the wafer is cut.
Only good dies are cut and moved to the next stage. Each die is inspected after cutting because dicing can introduce damage.
Now each die is placed and bonded into its module position. Electrical connections are made from the die to the module circuit.
The flex cable is bonded next, connecting the sensor to the phone board. If this bond shifts or cracks, the sensor loses its signal path.
Then the coupling layer is added to transmit sound between sensor and display glass.
Protective material seals the module against moisture and handling damage.
Before acoustic testing, the module is checked electrically.
Then the sensor fires its first pulses, and the echo pattern is measured.
Every pixel must respond with consistent strength across the full sensing area. Then, a test fingerprint is captured through glass to confirm real-world performance. Then the outside is checked for damage, contamination, and correct assembly. Good modules are sorted and graded before final packing. From raw silicon to sealed sensor, the module is ready to ship. But the sensors shipping today were designed years before this wafer arrived.
Inside, engineers chase larger sensing areas and faster recognition from thinner modules.
For Dr. Kwon, the hardest problem is reading detail through layers that keep changing.
Every phone model has a different display stack above the sensor.
So the sensor must be tuned for each phone's specific glass and display structure. Ultrasonic sensing also has to distinguish real fingers from fake ones. Sound waves capture depth, not just surface. That makes spoofing much harder. Most of that work stays hidden until the next sensor generation ships. At this scale, one particle on the sensing film can deaden a pixel cluster. Dead pixels mean missing detail, and missing detail means failed matches. That is why every step from deposition to dicing happens under strict contamination control.
Another challenge is keeping the piezoelectric film uniform across the full wafer.
If thickness varies, different pixels pulse at different frequencies, and the image loses consistency.
When the map shows drift, the deposition tool is corrected before the next lot runs.
Even the coupling layer must sit precisely, or signal strength drops at the edges.
Crosstalk between pixels is another enemy of image sharpness. Isolation structures on the die help keep each pixel's signal separate. A reliable fingerprint sensor is not luck. It is controlled film, clean process, and constant correction.
What hides under a screen begins here as wafer-level precision.
These sensors become the fastest way billions of people unlock their phones.
They also verify identity for payments, banking, and private data.
Beyond phones, fingerprint sensing is spreading into access control and personal devices. For many people, this sensor is the simplest proof that they are who they claim to be.
That is why a part this thin carries so much invisible responsibility.
She trusts the raw yield maps before she trusts the meeting summary.
A reference wafer helps prove the test tools are still measuring correctly. On this floor, one shortcut can become thousands of dead sensors.
Veteran engineers remember when fingerprint sensors were visible buttons on the front of the phone.
At home,
She unlocks her own phone the same way everyone does.
For her, that instant unlock means the process held.
From silicon wafer to working sensor, that is how fingerprint sensors are manufactured.
What surprised you most about the process? Tell us below.
Next, we enter another factory, where invisible precision powers daily life. Process Pulse Factory. Subscribe for the next process.